Welcome. We're going to take a look at composite functions. That's where we have a function in a function. So let's look at the first one. You think in your head while I go over these answers. So how many functions? We have y equals 2x minus 1 all squared. Well, let's find out. You think of the answer, and then I'm going to show it to you. How many functions? Well, there are, oops, 2. And what order do we evaluate? Right, so if we were going to evaluate, right, you would take care of the 2x minus 1 first, right, and then you would square, right? So like if you wanted to know f of 5, right, you would plug 5 in, you would multiply it by 2, subtract 1, and then square the result. What order are we going to derive? Well, we're going to take care of the square first, and then take care of the inside. How many functions do we have here? Y equals 2x times 3x plus 1 squared. Well, there are 3 functions. In what order do we evaluate? Right, well, we would take care of the inside, the 3x plus 1. Then we would square it, and then whatever we got, we'd multiply it by 2x. In what order are we going to derive? We're going to take care of the multiply by 2x part, then the square, and then the 3x plus 1. See if you notice a pattern here in the order we're deriving. We have y equals square root of x squared plus 1. How many functions are there? There are 2, right? We have the square root, and we have the x squared plus 1. In what order do we evaluate? Well, we'd plug in to the x squared plus 1, and then we'd take the square root of whatever we got. In what order would we derive? See if you figure out what it's going to be. We take care of the square root, and then the inside. We have y equals 1 divided by x squared minus 1 cubed. How many functions? You could say there were 3 if you called 1 one of the functions, but we could rewrite that as x squared minus 1 to the negative 3 power, right? So technically, that we could just call that 2. Right? In what order do we evaluate? Right? So first we would plug into the x squared minus 1, and then we would take the negative cube. What order are we going to derive? We're going to do the negative cube first, and then the x squared minus 1. And then we have y equals sine squared 2x. How many functions do we have there? Well, I hope you know that there are 3 there, right? There's the 2x, there's the sine, and then there's the square. And the square is on everything. Well, I'm sorry, I forgot to ask my question. What order would we evaluate? Right, we'd plug into 2x, we'd get a number, we'd take the sine of it, and we'd square. And what are we going to evaluate? Well, we're going to take care of the square first, and then the sine, and then the 2x. And if you notice, that last one's a pretty good example there. So notice that we're going to derive in reverse order of how we're going to evaluate. So rules for differentiation, we're finding the derivative of a composite function. All right, so we're going to rewrite the function f of x equals 2x plus 3 cubed. We're going to rewrite it as a polynomial, and then we're going to take the cube, and then we're going to learn an easier way to do that. Then we're going to take the derivative. Sorry, I don't know what I said, but we're going to take the derivative. Then we're going to learn an easier way to take the derivative than expanding. All right, so I have f of x equals 2x plus 3 cubed. That would be 2x plus 3 times. Now actually, if you remember, there was, let's use the rule rather than expand it out. Maybe that would be easier for us. All right, so if you, no, you know what, I'm just going to expand it out. Because I got to, no, we can do it. We'll use the rule. I changed my mind again. It's the middle of the day, trying to get this done. All right, let's try to use the rule. All right, so we have the 2x and we have the 3. And the 2x part is going to be cubed, and the 3 is going to be to the 0 power. Right? They're going to keep switching. And our coefficient is 1. The next coefficient is going to be 3. And the 2x is only going to be squared, and the 3 is going to be to the first power. And then we're going to have a coefficient of 3 again. But this time the 2x is only to the first power, and the 3 is squared. And then we're going to have a coefficient of 1, and the 2x is to the 0 power, and the 3 is cubed. So I took a little shortcut here. Rather than multiplying 2x plus 3 times 2x plus 3 times 2x plus 3, I use Pascal's triangle to remember that if I have something cubed, right, I remember what the coefficients are, and remember they're switching places, right? One is going to be to the third power and goes down in, the exponent goes down, and the other one, the exponent, is at the 0 power and it's going up. If you don't remember this, just multiply 2x plus 3 times 2x plus 3 times 2x plus 3, right? So this is going to be, so 2 cubed is 8. Of course, times 1 isn't going to do anything. So that's going to be 8x cubed, and 3 to the 0 power is just 1. So that's just going to be 8x cubed. Plus, right, so we're going to have 2x squared. So that's going to be 4x squared. And then we're going to multiply it by 9. So that's going to be 36x squared. And then we're going to have 3 squared times 3 is going to be 27. Times 2 would be 54x. And then we're going to have 2 to the 6th. Oh, that's 2 to the 0. My goodness, I can't read my handwriting. So that's just 1. So we're going to have 27. Now, I'll know if I made a mistake because my derivative won't work out when we go use a new and better way to find the derivative. All right, so this wasn't so bad because I took a little shortcut. Now let's find the derivative. So f prime of x equals, right, the derivative of 8x cubed, 3 times 8 is 24, reduce the exponent by 1. 2 times 36 is going to be 72, reduce the exponent by 1, and then 54, and the derivative of 27, derivative of any constant is 0. So okay, there's our derivative. All right, so now, Leibniz was the first of 2 great calculus developers to use the chain rule to differentiate composite functions. Let's write the chain rule together in the box below. You have the notes. I actually did the typing here. You add the notes to your notes. So where you see chain rule, actually you have this whole page in your notes. Where you see chain rule of differentiation of composite functions, so if that says if f of g is the composite function of y equals f of u, and u equals g of x, then the derivative of that composite function, the derivative of f of u, is going to be f prime at u equals g of x times g prime at x. In other words, we've got f prime of gx, the whole, times g prime of x, the inside. So our chain rule, dy dx, is going to be dy du, the derivative of the outside, the derivative of the whole thing, the outside part, times the derivative of the inside part. To show how this rule works, let's apply this rule to the function f of x equals 2x plus 3 cubed that we rewrote and differentiated as a polynomial form above. And if there's any mistakes, it was with my multiplying. All right, so we have f of x equals 2x plus 3 cubed. We're going to take the derivative of the outside. Right? So I like to call it BLOP. We're going to take the derivative of the BLOP cubed. Doesn't matter what BLOP is. And then we're going to multiply that times what we get when we take the derivative of the inside, which is 2x plus 3. And we're going to hope it's 24x squared plus 72x plus 54. All right, so now let's do it. All right, so the derivative of BLOP cubed is going to be 3 BLOP squared times the derivative of 2x plus 3. The derivative of 2x plus 3 is just 2x. Of course, let's fill in the BLOP. The BLOP was just whatever's on the inside, the 2x plus 3. So our derivative, f prime of x, is equal to 3 times 2x plus 3 squared, all multiplied by 2. Oops, I put 2x. Derivative of 2x plus 3 is just 2. Just 2. And actually, let's move that 2 in the front. So 2 times 3 times 2x plus 3 squared. All right, so that's going to be 6, and then let's square the 2x plus 3. All right, so that's going to be 4x squared plus, all right, so it's going to be 2 times 3 times 2, because there's going to be twice as many of them. Little rules here for Pascal's triangle. All right, so 2 times 3 would be 6, times 2 is 12x, and then the 3 squared, so plus 9. All right, and now let's multiply that out. So it equals, all right, so we get 24x squared plus 72x plus 54. And notice we got the same thing we got over before. I feel really good now. All right? Both with the fact that we have a new method for solving derivatives that are of composite form, and because I was perfect on my cubing. All right, so chain rule, derivative of the outside times the derivative of the inside function. We're going to use this every time we have a composite function. But maybe, and let's do one more, and then we'll do the chain rule again. And then I'm going to show you why you really want to use the chain rule. Why you really want to learn that. We have y equals 6x minus 10 squared. Right, so we're going to simplify and then take the derivative, and then we're going to just use the chain rule. Right, so this would be y equals, so the square root of, the square of 6x is 36x squared, and then it would be 6 times 10, or times negative 10, times 2, so that would be negative 120x, and then plus 10 squared, 100. All right, we'll take the derivative. dy dx equals, that would be 72x minus 120. Now let's use the chain rule. All right, so dy dx is 2 blop. All right, we're taking the derivative of blop squared. So derivative of blop squared is 2 blop. But hey, what's the blop? We need to take the derivative of the blop. Well, the blop is 6x minus 10. So we're going to take the derivative of the inside portion, the 6x minus 10. All right, so that's going to give us dy dx equals the 2, let's fill in the blop there, 6x minus 10 times the derivative of 6x minus 10, oops, the derivative of 6x minus 10 is 6. So that's going to give us 2 times 6x times 6, that's going to be 72x, minus, and then 20 times 6, that's going to be 120. Right? And you might say, hey, it really wasn't that hard for me to square, and then just take the derivative of that. Why can't I just do that all the time? Well, here's a good reason why you can't do that all the time. What if I change that exponent to the 15th power? I can't do that. I don't think I can expand. I'm going to be there a long time expanding Pascal's triangle for 15 rows and then multiplying all those out. I think I'll get lost, and I certainly will get lost if I multiply something by itself 15 times. So we really, so in the other example, if you expanded and then took the derivative, that's fine. But in this example, oh no, that would be awful, right? So if the f of g is the composite, where y, or the outside is f of u, and u is another function, right? We're going to take, our derivative is going to be the outside function times the derivative of the inside. Notice that when I'm taking the derivative of the outside function, the inside function stays just as it is, right? Blop doesn't change. Blop stays blop until then we take the derivative of blop. All right, so we have y, and that's why I put a blop up there, because you know what, students kept trying to take the derivative while they were writing the derivative of the outside part. No, the derivative of the outside part is just the outside. The inside stays just as it is. So I covered it up with a blop. So we want the derivative of y equals blop to the 15th power. dy dx would be 15 blop to the 14th power. And then let's move the blop. What's inside the blop? 6x minus 10. So notice 6x minus 10 does not change, right? And then we take the derivative of the inside. So we take the derivative of the 6x minus 10. All right, so we take the derivative of the blob. Oh, now I've written over it, so I can't cover it up. We take the derivative of the blob, and the blob stays just as it is, and then we take the derivative of the blob. So derivative of the outside, blob stays, then derivative of blob. And blob is my own terminology. All right, so we're going to simplify this as much as we can, which really isn't very much. I don't even know if I want to. Well, we'll combine like terms. That's about it. So we have dy dx equals 15 times 6x minus 10 to the 14th power, because we didn't take the derivative of 6x minus 10. I almost forgot about that. Derivative of 6x minus 10 is 6. Let's multiply the 6 and the 15 together, and then we are done. So that's going to be 90 times 6x minus 10 to the 14th power. Oops. And there we go. We have taken the derivative of that composite function using the chain rule. Let's do some more. I got lots. I think this lesson is 24 pages long. Let's find the slope of the normal line to the graph of f prime equals sine squared theta. And what I say, f theta equals sine squared theta when theta equals 5 pi 6. Oh, that's a tongue twister there. So f of theta, sine squared theta is the same as sine theta squared. The whole thing is squared. It's just a convention that we put the square there, but when we put that square there, we are saying the entire thing is squared. So the outside function is the theta, is the blob squared. The inside function is the sine theta. All right, just to make sure that's clear. All right, so the outside is the square, the inside is the sine theta. All right, so now we're going to take the derivative of the outside, and the outside, and I just call that one u. All right, so u prime is going to be 2 theta. Right, and we reduce by the exponent by 1, so it's just 2 theta. What's not 2 theta, 2 blob. Then we take the derivative of the inside. All right, so v prime, derivative of sine theta is cosine theta. So that means that f prime of theta is going to be 2 times the blob, which is sine theta, times the derivative of sine theta, which is cosine theta. And we'd be done, except we were asked to find the slope of the normal line. All right, so now let's find theta when theta is 5 pi 6. 5 pi 6 in the second quadrant. This right here is the leftover pi 6. That's the same as a 30-degree angle. This is the 30, 60, 90 triangle. Opposite the 30-degree angle is 1. Along the x-axis, opposite the 60-degree angle, is negative square root of 3. It's a negative because we're in the second quadrant. And 2 is the hypotenuse. So then sine theta, or sine 5 pi 6, I should say, is going to be 1/2. Right? So now we're going to plug that in. Actually, we're going to plug it in over here. All right? I'll write it over here, and then we have to plug it in over into the derivative. We're also going to need cosine, right? Because we have a sine to plug into our derivative and a cosine to plug into the derivative. So cosine 5 pi 6 is going to be negative square root of 3 over 2. All right, so now let's plug those in to find the slope, but we know when we plug into sine what we're going to get, and cosine what we're going to get. All right, so f prime of 5 pi 6 is 2 times sine 5 pi 6 times cosine 5 pi 6, and we know that would be 2 times 1/2 times negative square root of 3 divided by 2. All right, so the 2 and the 1/2 will cancel. That's just going to be negative square root of 3 over 2. That's the slope of the tangent line. if we want the slope of the normal line, remember the normal line is perpendicular to the tangent line. So it's going to be the negative reciprocal. So then the slope for the normal line is going to be positive, and it's going to be 2 over the square root of 3. And if you want to rationalize it, it would be 2 square roots of 3 over 3. I'm fine with either one. Right? And we've got this one done. And that's all we were asked, just find the slope of the normal line. All right, so here we want to find the derivative of blop to the 10th power. So that would be the derivative of the outside would be dy dx equals 10, whatever blop is, I'll fill it in, to the 9th power. Wait, forgot what I was writing there. To the 9th power times the derivative of the blop, whatever the blop is. All right, let's find out what the blop is. The blop is 3x to the 4th plus 2x minus 9. So the derivative, dy dx, is going to be 10 times 3x to the 4th plus 2x minus 9 to the 9th power. The derivative of that, so we're taking the derivative of 3x to the 4th plus 2x minus 9. And we're going to multiply it by that. So dy dx is 10 times 3x to the 4th plus 2x minus 9 to the 9th power times the derivative of 3x to the 4th would be 12x cubed. Derivative of 2x would be just the 2, and that would be it. And this is okay the way it is. I think maybe I distribute the 10 to the things without the exponent on it, and so then it would be, in parentheses, 120x cubed plus 20 times 3x to the 4th plus 2x minus 9 to the 9th power. That would be as much as I'd simplify that. All right, anything beyond that would just be way too much. All right, we're not raising something to the 9th power. All right, so let's take a look at this one. All right, so here we're taking the derivative of y equals 1 over x squared minus 1 cubed. All right, we've got a function raised to a power. That is going to be the chain rule. We don't have to use a quotient here. We could just rewrite that as y equals x squared minus 1 to the negative 3 power. All right, so now we take the derivative of the outside, right, which is the blop to the negative 3, and then we multiply that times the derivative of the inside, which is x squared minus 1. All right, so dy dx, actually I'm just going to make this the whole derivative, right, because we're showing multiplying by the derivative of the inside. So dy dx is going to be negative 3 times x squared minus 1 to the negative 4 power. So we'll use the power rule because it's just something to the negative 3 power. Just consider it anything at all to the negative 3 power. And then times the derivative of the inside. So the derivative of x squared minus 1 would be 2x. And then let's just simplify that. So dy dx equals, so in the numerator we'll have negative 7x, in the denominator we'll have x squared minus 1 to the 4th power. And there we go, there we have the derivative. That's all there is to it, once you know the quotient rule. All right, so these are in your notes, and I have only so many minutes left before lunch ends, so I'm going to do what I can, and then whatever I don't finish is going to be on the next video. Find the derivative of each of the following functions by applying the chain rule. So f of x equals 3x squared plus 2 all cubed, right? So the outside is blop cubed. The inside, let's write it as b. The inside part is 3x squared plus 2. So f prime of x is going to be the derivative of the outside. That would be 3 blop squared. And what's the blop? It's 3x squared plus 2. And then we're going to take the derivative of the 3x squared plus 2. What's the derivative of that? Is just 6x. So we're going to multiply this by 6x. All right, so now let's combine the like terms. So f prime of x equals 18x times 3x squared plus 2 all squared. And there we go. Another one done. Let's just go right across. All right, so we have a square root. G of x equals the square root of 2x plus 5. We do have to rewrite that as a rational exponent. So g of x equals block to the 1/2 power. We're going to take the derivative of the outside, which is block to the 1/2, times the derivative of the inside. The inside is the 2x plus 5. All right, so g prime of x, actually let me use a different color so it doesn't all blend together. Yeah, I have started this in green. I don't know why I didn't pick up the green pen. So g prime of x equals, all right, so derivative of the outside, blop to the 1/2 is going to be 1/2 times blop. What's the blop? The blop is 2x plus 5. And we're going to reduce the exponent by 1. 1/2 minus 1 will be negative 1/2. And then times the derivative of the inside. The derivative of 2x plus 5 is just 2. All right, so we're taking the derivative of the outside times the derivative of the inside. The 2 and the 1/2, that's just going to be 1. So g prime of x is just going to be 1 over the square root of 2x plus 5. That's it. Everything else canceled out. All right, so on the next one, we have h of x equals the cube root of x plus 2 all squared. We do need to rewrite that as a rational exponent. So h of x equals x plus 2 to the 2/3 power. We're taking the derivative of the outside times the derivative of the inside. So a really easy derivative. All right, so we have h prime of x equals 2/3 blop. What's the blop? It's x plus 2. And then 2/3 minus 1 would be a negative 1/3. And then times the derivative of x plus 2, that's just going to be times 1. So we don't really need the 1. So now let's just simplify this out. So h prime of x equals 2 in the numerator. I'm going to change that back to a cube root. I think that looks a little nicer. And then 3 cube roots of x plus 2. There we go. And then the last one on this page, I think I can get this one done. Oh, I have to go quickly. F of x equals 5 times the cube root of x squared plus 2x. Let's rewrite that as a rational function. So f of x equals 5 times x squared plus 2x to the 1/3 power. All right, so the outside function is 5 blop to the 1/3. The inside function is x squared plus 2x. All right, so f prime of x is, so the derivative of 5 blop to the 1/3, that's going to be 5/3 blop. What's the blop? It's the x squared plus 2x. And then 1/3 minus 1 is going to be a negative 2/3. The derivative of x squared plus 2x is going to be 2x plus 2. All right, so let's simplify this out as best we can. All right, so f prime of x equals, so 5 and the 2x plus 2 stay in the numerator. Let's just make that 10x plus 10. And in the denominator is going to be the 3. And then, oh, I guess we'll write that back as a radical. All right, so that's going to be in the denominator x squared plus 2x, and that is squared, and don't forget the 3 on the radical. All right, so it's f prime of x is 10x plus 10 divided by 3 times the cube root of x squared plus 2x squared. Right? And so now you've learned a little bit about the chain rule. In the next video, we'll see some more. All right, thanks for watching. Bye for now.